Good morning, everybody. How was the weekend? Yeah? Was it Comer? Anybody? All right. Roll sheet. Send it around. We'll start this side this time. What to do with that? Let's see. Okay, so this is how I give your labs back. Okay, there's two folders, right? There's an 8 a.m., what I call the section 1, and then there's 11 a.m., right? There should be 2 labs in here, okay? The grades are already up on Canvas. Just send them around and pull out the 2 that are yours. Try not to mix the folders up, and try to get the folders to go up and down each of the rows as much as you can. On lab 3, the one we did last Thursday, if you don't see any other mark than the magic mark I gave you, it's a 10, right? I just don't bother to waste the ink on that, okay? If I had to change your score for any reason, it will be indicated. All right, let's see. Jacob, which section are you in?
No one.
All right, start this one over here. Again, if it's not yours, just pass it on. All right, so that's how I do that. We don't see each other next Monday, right? Right? Day off? So what does this week and next week look like? So today and Wednesday we're going to do chapter 4. It's a big chapter. It's like a coming together of kind of everything. Some of you have expressed that you're worried, like, I'm not getting this stuff, Mr. Balogh. It's going too fast. Chapter 4 is your shot at redemption. It's kind of everything comes together with the vectors, with the kinematics and our toolboxes. And it's a little bit of like, I mean, it's a couple new things, but a lot of it is like we're doing the same things over and over again. So I'm hoping that it starts to sit a little bit better. If it doesn't, we need to do some intervention. So that's this week. Your chapter 3 homework is due what, this Saturday? Is that right? And then chapter 4 homework is due next Wednesday. But of the 2 chapters, chapter 4 is bigger. So I really strongly suggest that you try to get chapter 3 homework done by tomorrow or Wednesday. And give time for chapter 4 homework to happen. You just need time on that one, okay? So that's kind of the pacing there. It feels a little bit awkward, but that's because this Thursday we're doing a lab, but the Thursday after that, what are we doing? An exam, right? So we got to get ready for that. We don't have Monday together. But on Wednesday of next week, we're going to do a exam review. That situation is one where you come to me to ask questions. I'm not going to give you anything on that day. And if you don't ask me questions, I'll just stand here and make bad puns and dad jokes or something, okay? So to prevent that, you need to ask me questions. I have been giving you a lot of material in lectures and in homework, right? And this is your chance to just get whatever questions you want. We'll talk more about sort of the format of the exam on that day, maybe a little bit on Wednesday just to give you some heads up, and we'll roll into the exam. Okay? Questions, comments, or concerns about sort of where we're at and what we're doing? Cool. All right. Let's jump into chapter 4. Now, we did spend some time learning about vectors and how to add and subtract them and do the unit vector kind of thing. How does that factor into our toolbox, our list of kinematic equations? In chapter 2, because we didn't have the language of vectors, we kind of went easy on you. But in reality, our toolbox does have vectors in it, right? Things like velocity and acceleration are vector quantities. And so we need to make sure we understand, right, that they have magnitude and direction. Now, I'm going to use delta x. Some books use delta s as a generic sort of thing. Actually, you know what? I'll go really physicsy on you, and I'll use an r. You're like, oh no, Mr. Balogh, what's happening? Don't worry, it's not a radius. It's just a generic distance. But I'm hoping as I write these down that you are you're familiar with them, you recognize them from that toolbox. It's just we've thrown all the vector signs on top of things. In reality, there are 9 equations there. Why 9? Not quite.
I think it might be repeating.
Say, repeating. How many directions could the velocity be pointing? X, Y, and Z. We typically don't do Z in here, so you don't have to panic about that, right? But really, that final velocity on the first equation could be in the X direction, the Y direction, and the Z direction. The same thing can be said for the initial velocity and the acceleration, right? So the first equation can really be written 3 times in each of the different directions in the Cartesian coordinate system. Same thing can be said for the middle equation. Same thing can be said for the third. So really, I've got 9 equations on the screen. In practice, okay, we tend to write down all of these equations with a subscript notation that's a little bit easier for our human brains to latch onto. For example, I might write v sub x. Notice I'm not writing a vector sign over the top of that. Okay? It's still got vector properties like direction, but I'm indicating that I'm only talking about the x direction now. And then I would write v naught. Now, what do you think vx means?
Velocity in the x direction.
Close. Which velocity?
Horizontal.
The final velocity, right? Because one's the initial velocity? The one with the knot on it, right? Okay. But notice it's an initial velocity in the x-axis, along the x direction, right? And then ax, what's that? Acceleration in the x direction. So you're being very specific here, okay? And then we can also write this as Vy equals V naught y plus Ay times t. So, and I'm not going to write the z one down because we're not going to use it in this class, but we can keep going with this, right? And so in that sense, these equations, this toolbox is a very compact way of writing 6 to 9 different equations that we can all use individually. So let's leave that for a little bit and talk specifically about what we're going to be doing in this chapter. Okay? A projectile. What's a projectile? Think physics, like what you might have read in the book. Something undergoing projectile motion. What's true? Well, they do follow parabolic paths, but for a very specific reason. Let me give you a hint. It's the same reason that we had back in chapter 2 for vertical objects that were being dropped. Gravity is the only thing that is acting on it. The only force, the only acceleration that an object in a projectile motion is going to have is going to be gravitational acceleration. And so in chapter 2, we only threw the ball vertically up and down, right? Or maybe we dropped it, right? But the point is, it was all happening in one dimension. What we're going to do now, we're going to take this thing and we're going to give it both sideways and vertical motion, right? But critically, what can you tell me about the acceleration in the vertical direction? The acceleration in the y direction is going to be one thing and one thing only. You know what? I'll write this, just for right now, as negative g, which is equal to negative 9.8 meters per second squared. What is little g? It's a number, right? It's 9.8 meters per second squared. Does little g all by itself have a plus or minus sign on it? No. It's just that number, right? It's a shorthand, so you don't have to write 9.8 meters per second squared all the time. You just write g, right? And be done with it. Notice that I stuck a negative sign on AY. I said the acceleration in the y direction is pointed which way? Down, negative, right? And has a magnitude of 9.8. That's what I'm trying to say there. Very specific, okay? So, what does that imply for the acceleration in the x direction? If projectiles are in free fall, so is this ball in free fall the entire time it was out of my hands?
Yeah.
Yes. Does it matter if it's going up? Does it matter if it's going down? The only thing that acted on it, right, was gravity after it left my hand and before it hit my hand. Okay, let's see if I can do this. It's been a whole summer and a little bit more, okay, right? Let's see if I can juggle these, right? Okay. So, what can you tell me about each of these balls when they are not in my hand? They're in free fall. We ignore air resistance, which is pretty safe here because they're not moving very fast and they're kind of heavy, right? And yes, I can juggle and lecture at the same time. Okay, right? As students, you need to do more, right? As students, you often feel like you've thrown all 7 balls in the air and you're just waiting for which one's going to come down first, right? That looks like you logging into Canvas and just hitting the first thing to do, right, as you go down. But all of these were in free fall the instant they left my hand and before I caught them. Because when they're in my hand and when I'm catching them, is gravity the only force that I've got? No, I've got my hands and other things, right? So what is the acceleration in the x direction going to be? It's going to be 0. Okay? We're not going to let things accelerate in the x direction. We could. This is the level where we could introduce some of those ideas, but we got bigger fish to fry later, so we're going to save some time and move on. Not have to worry about that too much. So, what does that mean that we can write down? So we've got 2 directions, right? We've got an x direction, we got a y direction. So we can write down x equals v naught x plus ax times. That's the first one, right? Just written in terms of x's. And then we can have delta x v naught xt plus 1/2 ax, that's supposed to be x, it wasn't very good, xt squared, and v naught x equals 2a delta, ax delta x. Are you required to memorize the kinematic equations? No. Have you memorized them yet? Maybe. Right? Like, you use them enough, right? And they kind of start to stick. Even for my brain that can't memorize anything, they are just seared in there. For the y direction, right, we do exactly the same thing, but we just put y's on everything, right? So delta y instead of delta x, v naught yt equals 1/2 ayt squared. And then vy squared plus, equals, not plus, equals v naught y squared plus 2ay delta y. Okay, so there we go. We've got the toolbox written out. These are the same tools, like the second equation in x and the second equation in y are the same tool. It's just that the handles are different colors, right? But they're both screwdrivers. Okay, so if we assume projectile motion, right, where ay has to be equal to that and ax has to be 0, what happens to the x toolbox? What happens to the first equation if ax is 0? That term disappears, doesn't it? And what does it say now? The final direction in the x direction is equal to the initial velocity in the x. Well, duh. It's not accelerating, right? So it's going to start and end with the same x direction velocity. Okay. What's the third one say? Same thing, doesn't it? Oh, just got nasty square roots in it this time, right? Okay. But because there's no acceleration, we expect the velocity before and after to be exactly the same. The middle one gets a little bit more interesting because it actually produces an equation that we can use, right? It says that my horizontal displacement will be equal to my x direction velocity times time, which of course is kind of a definition. I mean, velocity equals distance divided by time. And if I rearrange that equation, I get that. So really the only useful tool that falls out of our toolbox when we apply the special conditions of projectile motion in the x direction is that one. Kind of nice. All right, what happens in the y case? Does anything get fixed for the y toolbox? Not really. And this is where your book and I are going to differ slightly to the, I'm sure, frustration of you guys, okay? Because your book would write the, let's do the second equation. Your book would write delta y equals v naught yt minus 1/2 gt squared. And it might go one further that I'll talk about here in a second, okay? What did your book just do? It stuck. It substituted ay for negative g, didn't it? Right? Which is perfectly valid. I don't have much of a problem with that, except for the fact that that's not going to help you in the future. It might help you right now, but it's certainly not going to help you in the future. And it might do one more thing. Let me see if I can't help you understand what's going to go on. If we launch an object, let's launch something, I don't know, at some angle theta with some speed v naught. 10 meters per second, something like that, right? Is that 10 meters per second pointed in the x direction? No. Is it pointed in the y direction? No, it's pointed in both, right? And now that we know chapter 3, what can we do with this vector? Break it up into its components, right? We could find the v naught x, the side that's touching this angle, sine or cosine? Cosine. So that would be v naught cosine theta. And then the side that's not touching the angle, v naught sine theta, which would be our v naught y. Now that's exactly what we're going to do. We're going to treat two-dimensional problems as two one-dimensional problems happening simultaneously. Instead of having to deal with the vectors all the time, we're going to break that vector up initially to its x and y pieces and then use the parts of the toolbox that apply. In other words, am I going to use v naught y over here in this equation? No, because that's just an x direction equation, right? So your book, though, and other places on the internet, and again, they're not wrong. It's a perfectly legitimate thing to do, but in terms of you learning how to use this stuff, I feel like this is a real handicap. Instead of v naught y, they'll write in v naught sine theta into their equation. And again, what have they done? Is this a new tool? Okay, many of you are looking at me like, yeah. I mean, look at it. It doesn't. You're telling me that this thing and this thing are the same thing? I would say yes. Do you see how they've buffaloed you into thinking that you're learning something new? When in fact, what we're doing is we're using chapter 2 twice per problem. We've been through chapter 2. We might be a little bit shaky still on chapter 2, but I'd really like you to see these problems as chapter 2 problems with the additional lifting that we've got to do of breaking them up into one-dimensional problems first and then going for it, which is why you won't see me write this down. I stick with those toolboxes up there because they look familiar, and I also can't remember stuff. I don't want to have to remember a brand new set of equations because they really aren't brand new. They're the same kinematic equations with all the same powers and limitations that we discovered in chapter 2, written out in specific directions. So if I can do chapter 2 problems, I can do chapter 4 problems without thinking that there's a brand new set of kinematic equations. So I teach you that, I show you that so you can see why things might look so different if you're watching one YouTube video and then you read the book and then you look up a different web page or something like that, okay? They're going to look different, but in fact they're the same. Just because there's lots of different ways of writing this stuff down. And wouldn't it be great if we could all agree on one way of doing things? But if you've taken any look at the news, you know that one thing that human beings can't seem to do is agree on anything. Right? So, it's no surprise that even in science, where fact and fact, truth is truth, we still have different ways of writing it down. Okay, so let's do this. Okay, I need an object that you want to see launched off of a cliff. A what? A tomato? Is that what you said? What do you have against tomatoes? Fine, a tomato. We're gonna launch a tomato off of a cliff. Let's see. Did I pick numbers for this one? I might have picked numbers for this one. I did pick numbers for this one. Okay. So this is the situation we have. Okay. We have a 75-meter tall cliff overlooking a body of water, the ocean, something. Okay. And we're going to launch this tomato. Did it matter that it was a tomato? Makes absolutely no difference. That's why I let you guys pick. We're going to launch this tomato at an angle of 50 degrees with a speed of 40 meters per second. Let's figure out everything that we could figure out about this situation. You'll notice here I didn't put like a word problem up on the screen. Okay? This is a situation we could be launching something and what's something that we might want to know or figure out? I don't want to figure out anything, Mr. Bailey. You can't make me do this. Yeah.
Find all our initial velocity.
Okay, we'll get there. But like at the end, what's something we could want to know? How far it went, like horizontally from that point, right? Okay, like that's called the range of the projectile, right? How far it went. No, I heard another one out there. How high, like what is its maximum height above the launch position or above the water? Okay? What else could we maybe want to know? How long was it in the air? You guys are just going through the toolbox, aren't you? Right? We can find time, we can find accelerations, we can find the initial parts, we can find the final velocities of things, right? So let's just go for it. You know what? Because we're gonna need to repeat it a lot. I'm just gonna put the toolbox up here on the board. Okay. I tend to write the chapter 4 toolbox pretty much exactly the same way I write my chapter 2 toolbox. It's just I put y's on everything, right? Because the y equations are the ones that survive. B naught yt plus 1/2 ayt squared. I always forget the t squared. By squared equals b naught y squared plus 2ay delta y. Okay, so those are all the y ones. We've only got one x one, don't we? It was delta x equals v naught x times t. That's really kind of the only addition, if you want to think about it, in the chapter 4 series of equations. But it really comes from the chapter 2 setting the acceleration, equal to 0. So there we go. Here's our toolbox. Everything we could know and not know, which is where I'm going to start. I'm going to start and I'm going to look at my tools and go, look, okay, I could know Vy, which you should be thinking in your head means what? What velocity is it? The final in what direction? Y. So this is the final velocity in the vertical or y direction. Right? You want to think that as you write it down. It's not just Vy, it means something, right? Okay, what's V naught y mean? Good. Initial velocity in the y direction. AY, the acceleration in the y direction. T doesn't have an x or a y, it's just t, right? So that's just time. I can tell already I'm going to run out of room for this list. Mr. Balogh needs to plan better. Let's do it over here. Okay, and then what comes after t? Delta y. Delta y. What's delta y? Conceptually, what is it? It's a displacement. It's a change in height from where I start to where I'm trying to figure stuff out. Okay, whatever that means. VY, AY, got all those. Just repeating. Got all these things written. Oh, I'll pick up a couple new things, don't I? A delta x and a v naught x. Delta x being the horizontal range, and v naught x being the initial velocity in the x direction. Okay, so that's the list of things I could know and not know. What do I know?
V naught x, V naught y.
We know v naught x and v naught y? Well, at least we can find them, right?
Yeah.
Given a vector, what are we going to do with it? Find its components, right? So can you tell? So what is v naught x going to be? 40 cosine 50. And how did you know it was cosine? It's touching. And v naught y is going to be 40 sine 50 degrees. So I can go and calculate those, which I think I did. Let's see if I got them right. I got for v naught y, I got 30.6 meters per second. And I stop. I've written a number down. And what should we always ask our numbers? No. Okay. More important than any of those things? What sign is it? What direction does it have? Is it going right or left? It's going to the right. I've drawn it going to the right. Okay? It's sitting right here. Is that the positive x direction? Yeah. Oh, wait, I was doing y. Is it going up? Yes. Okay, is up positive for now. Okay, so positive 30.6. So I'm going to put that on there. I'm going to put the positive on there because future me is going to come back and go, what the heck was I doing? What was I thinking? Right? And at least that's an indicator that I checked the direction. I might have gotten it wrong, but at least I tried. Okay. Okay, so we know v naught x is positive, what did I say? I didn't say, 25.7 meters per second. Okay, so I just did those got the things in my calculator. All right. Do we know anything else? Do we know the acceleration in the y direction? It's negative g, isn't it? Negative 9.8 meters per second squared. Okay, that's good. All right. I think somebody earlier said we know delta y. Do we know the vertical displacement of the projectile? So we know that this projectile follows this parabolic path. If you read the book, you learn about the parabola. Basically, it's the mathematical function that fits all of these conditions when you have just gravity. Okay. What's delta y in that picture? Okay, it's the 75. Okay. But Emily, what did you say? Negative. And why is it negative 75? Final minus initial, we could argue to the cows come home over where we're going to put 0, but it turns out it doesn't matter where you put 0. You will always get negative 75 because it went which way? The net motion was downward. A lot of you are sitting there go, but Mr. Balogh, it goes up first. Yes, I know. And so does the toolbox. It knows all of that. but we need to give the toolbox the correct information. And delta y is a comparison between where it starts and where it ends. Everything else you don't need to worry about. It's going to worry about. So between where it starts and where it ends, it went which way? Down. How far? 75. So down is negative, and then we put the number in. There was a hand out there somewhere. I missed it. No, we're good? Okay. So those are the things we know. Do we know the rate? Do we know delta x? No idea what delta, but let's just draw the picture where delta x would be. Delta x would be this distance. I see sometimes, don't draw this, I see some students trying to draw this distance right there. I could care less what that distance is. It doesn't mean anything, okay? Because it's going in both the x and y direction, okay? And it's usually not very interesting to know, okay? Delta y is vertical. Delta x is the horizontal distance it goes, okay? All right, and I drew it down there. I could just have easily have drawn, again, don't draw this. I could easily have drawn my delta x up here, right? Okay, doesn't matter. We tend to draw it down at the bottom so it's not in the way. Go away thing, okay. All right, we don't know what delta x is. Do we know the time? No. Should write down that I've thought about these things. I don't know. Vy. What's Vy again? Final velocity in the y direction. Where does Vy happen? It's right at the end, right before it hits the water. Okay? Right here, we will have a Vy and we'll have a Vx. Now, we know something about Vx. What do we know about Vx? Same as V naught x, right? Those are the same. Okay? The Vy will be down there. Okay, so we don't know what that is. It's not zero because once it hits the water, that's not projectile motion anymore. It's not in free fall. It's going to work. Okay, so okay, we can find it, but we don't know time. Right? So let's say we wanted to find the time. Okay, let's say nothing else matters, we just want to find the time. Can we use the third one? Doesn't have time in it, right? Can't use the first one because it's got two unknowns in it, right? Time and Vy. So, oh, by the way, what step am I doing now? This is the planning stage. This is the strategize step, right? I've visualized by making a list, drawing a picture, doing whatever it takes for me to organize my information. And now I'm moving on to the let's apply physics part, okay? And really try to figure out what's going on. I've been applying physics all along conceptually, but now I've really got to get it in the language of math. And so I'm staring at the second one going, okay, I know my delta y, I know my v naught y, I don't know my t, but that's good, and I know. So everything is known in the second equation except the time, right? So my plan becomes use the second equation and solve it for t. Why do I not want to do that? Uh-huh. This is quadratic in t, isn't it? So if I use this second equation, I got a t and a t squared in it, don't I? And that means quadratic. And if I'm going to do a quadratic, I'm just going to put the numbers in because solving quadratic symbolically is just, it's a pain. It's an absolute pain. Liam, did you have a question?
No, we use the first and third formula.
Yeah, you let the secret out of the bag. Let's do this first.
Okay.
What was I doing? 30.6 t minus 4.92. Ah! Where'd the minus 4.9 come from? It's a half of 9.8. I've written half of 9.8 so many times in my life, I've given up. And I just write 4.9 now. Okay, with the minus. So when you see that happen, that's what I did. I took the half, multiplied by 9.8. We're done. Okay. All right. I was taught by my math teachers, assaulted by my math teachers, insulted by my. I'm not sure which. That you always have to get the squared thing on the positive side of the equal sign. It's not true. It's not true. I found out later it wasn't true. I was so mad. Okay, but it's been drilled into me now that this is what you do. Okay, and now what's my A? What's my B? Negative 3. And what's my C? Negative 7. Okay. What do you do now? Cry. Change your major. Right? Do something else. Because you know it's going to happen when you try to plug it into the quadratic formula, right? Yeah, there's going to be a syntax error somewhere. You're going to get imaginary numbers for a while. Your TI calculator is going to hate you because of parentheses or something like that, right? Okay, now, so this is what we're going to do. We're going to go to Wolfram Alpha. Okay. And we're going to go, does anybody know what Wolfram Alpha is? You're going to know now, okay? This is Google for math, right? And physics and a bunch of other things. But we're going to solve, what are we going to solve? 4.9 t squared minus 30.6 t minus 75 equals 0 for t. It did something. What is that? What is this? It's called math. Let's do approximate formula so it does something real. Okay. 2 answers, right? Really zoom in on those answers, okay? 2 answers. Why 2 answers? Plus or minus, right? Quadratic, the square roots are involved. Okay, fine, right? Which one do I pick? Why did you pick the positive one?
I can't be negative.
It can't. Because I can flip the sign of these answers very easily by just doing a slightly different setup. I don't want to get into the weeds about this too much, okay? So just trust me that this can lie to you. Depending on how the problem is set up, you could end up with valid answers of positive 1.8 and negative 8.12. And if you pick the positive answer in that case, you will be wrong. It has nothing to do about which one is positive and which one is negative. Let's look at this a little bit deeper. What do we know about the motion of our projectile? Bigger? Why did we get 2 answers? Don't draw this on your screen, okay? This parabola continues over here, doesn't it? Okay? And we asked mathematically, when is the ball at negative 75? And mathematically, it returned 2 answers. Because that's math, right? But we know one of these answers isn't real. Which one isn't real? The answers were negative 1.8 and 8.12 seconds. Which of those is not real and why? Notice, one of them's big and one of them's small in magnitude. You're really, really close. I think you even got it right. The 8.12 seconds is describing this part of that parabolic path. How do I know it's describing that part and not the shorter part over here? Because it's the longer of the 2 answers, right? The 1.8 seconds is for this shorter section right here. Is that one physically possible? Is that what physically happened? No, okay? But the 8.12 describes the further path, right? The total part of this parabola that this object is going through. The reason I'm teaching you this is because it's not about which you were taught wrong when you said the positive answer going. The positive answer depends on what direction you call positive. Okay? What matters is we got an answer that had 2 times in it. One was a longer time, one was a shorter time. When would you ever use the shorter time? What if you had a situation where instead of throwing it off the cliff, instead we threw it downwards at like an angle of 70 degrees, right? Mathematically, we are now describing a parabola that looks something like that, right? But what's the real part that we are concerned with? This shorter part, right? And whatever signs we get on the quadratic, we would just pick the smaller magnitude answer. Time does always have to be positive, but that doesn't mean the math's positive answer is going to be the right choice. Did I just buffalo everybody? Okay. I taught you truth at the risk of confusing. For those of you who want to live the lie, pick the positive answer. If you set positive up and positive to the right, the positive time will be the right answer. I'm just pointing out that as we go through this class and we start defining directions, positive being down and stuff like that, that's not always going to be true. Yeah?
I just had a question. So on the problem that showed on the Wolfram, the problem with...
Yeah, I know. Yeah, I know. Oops, that didn't work. This one's the control of the screen. Yeah, see it? Yeah, you can't. I hate math. Okay? I just do, right? Because mathematically, this parabola and what I drew for you is exactly the same. Okay? This is where part of this confusion comes in. Okay? So, I don't want to spend time on showing you that right is one thing or the other. But just always be a little bit suspect of just picking the positive answer. Do a little bit more due diligence on thinking about what it's telling you. All right, Liam, how do we avoid this problem?
We're going to use the first formula. And then
Okay.
We're going to isolate for t.
There is another way, right? So we can do this and get the same answer by going through a different method. This third equation, what can the third equation give us? Do we know delta y? Yeah. Do we know ay? Yes. We know 2. Do we know the initial y velocity? Yes. So what can we find? The final y velocity, right? Okay, that might be something we want to know. I've got it up there, Vy, right? We can find Vy, right? But now that we know Vy, what could we use to avoid the second one in its nasty quadratic? I think that's the first one, right? Now we know this, and so that means we can solve for time. Okay, so we avoid the quadratic. What are the traps that are laid for us? We have to be very careful about our signs. We are doing 2 equations, not 1, so there's more opportunity for algebra mistakes, right? Neither of these is favorable. It just depends on how your brain works and your skills and what you're more confident in doing. Some of you love the quadratic and can do it no problem. I'm amazed at you. Quadratic has always been a nemesis of mine, right? So how do we go? So and pick that answer for the time. But let's do it the other way here. Purple, right? We're going to use the third equation to a delta y, then the first equation. Solve for t. I wrote down my plan that time. Okay. So using this third equation, this is going to be Vy is equal to the square root, because I got to take square root both sides, V naught y, which is 30.6 squared, plus 2 times a negative 9.8. I'm starting to panic. I can feel the anxiety rising because what do I have now? A square with a negative thing in it. Imaginary. Oh, good. Okay. that problem fix itself, right? Because a negative and negative are going to be a, all right. So, did I do this? I got 49. I got this as plus or minus 49 meters per second. Which one is it, plus or minus? Why is it minus? It's going down, right? If you say positive 49 for the final y velocity, what are you trying to tell the toolbox? It was moving up when it hit the water. That's not possible. So it's really important that you nail the sign, right? If you're going to do it this way. Okay, so negative 49. Now that I've got that, I come up here and I put it into the first equation, equals v naught y 30.6 minus 9.8 times t. I solve that for t, and lo and behold, I get 8.12 seconds. By doing it both ways, what have I just done? I've checked my answer, right? Okay, so check it, step done, right? These two are in agreement, and that makes me happy. Okay. How do we find out how far it went sideways? This is what you get if phones ring. You get me dancing. It's very bad. You don't ever want it. No problem. Oh! Delta X! We've only got one equation, right? Do we know V naught X? Do we know T? Can we find this? Delta X, V naught XT equals V naught X, which is 25.7 times 8.12, which gets me 208.7 meters, not meters per second. Okay, so there's my total range. All right, height above the water. Height above the water. What do we know? Well, okay. Do we have the delta x and delta y for maximum height? Where does maximum height take place? If I gave you the pen and told you to write the point, where would you put it? Right, okay, where velocity is 0 is wrong, kind of. Where the y velocity is 0, because the x velocity doesn't change, right, in projectile motion. So does the ball, the tomato, have speed at max height? Yes, it's moving sideways. It hasn't stopped. In the vertical direction, it has stopped, right? So at the maximum height, we know that Vy is equal to 0. Now here's something I know confuses everybody all the time, but you can count on this. You can take this one to the bank. If you tell this toolbox that a velocity is 0, vertical, hopefully not horizontal, but vertical velocity is 0, there is only one place where the vertical velocity can be 0. Where is that place? Maximum height. It's the only place vertically where the object stops moving. If we threw this thing off horizontally, you're going to have a problem like that in your homework, where they launch something horizontally. I think it's a tennis ball or something, okay? Right? What is the vertical initial velocity? 0. What does that mean for the height of the tennis ball? It is the highest it will ever be. When you put a 0 in for a vertical velocity, you are telling the kinematic equation that is the highest point. So if we come over here and we write Vy equals 0, okay? Does this list work anymore? Is our delta y negative 75? No. Because delta y will be what now? It's going to end up as a positive value. Because the ball at maximum height will be higher than where we launched it. It's higher than where we launched it because we threw it up at an angle of 50 degrees. Is delta x going to be whatever it is, 208? No. We don't know how far sideways it goes before it gets to maximum height. Is the time going to be 8.12? No. We got a different problem here, don't we? So we have a different list. What's the only thing that really we know? We know acceleration in the y direction. Okay? So, if all we know is the final well, we know the initial velocity, right? Did that change? Was our launch speed any different? No. Okay? So now, if we want to find out what that delta y is, which equation would we use? Do we know how long it takes to get to max height? No. So which one are we going to use? Third one. Doesn't have time in it, right? Do I know this? Do I know Vy? Yeah. Do I know V naught y? Yeah. Do I know Ay? Yeah. Do I know delta y? But I can find it. I can do algebra, right? And now we solve for delta y, which is going to be Vy squared minus V naught y squared over 2a. And we get, I got 47.8. I got a positive 47, Mr. Balogh, 0.8 meters. So I type that into Wiley Plus and it turns red. 47.8 is not the max height above the water. It's the delta y. It's 47.8 meters above the launch point, right? Delta y is always a comparison between where we start and where we end. We started at the launch point, we ended at max height. So what's the height above the water? 75 plus the 47.8. 122.8. That's a good example of how you can be totally right and still have Wiley Plus tell you it's wrong. Gotta see what they're asking for, right? A lot of times, physics problems, textbooks, they're not real careful. They try to be, but they forget. They'll just say, what is the maximum height of the projectile? Like if you're launching it off of a cliff or something like that, right? If they ask you for maximum height, that is always from ground level, not necessarily the launch height. They'll say, what is the maximum height from the launch point, if they just want the 47.8, right? But in general, we're doing everything from ground level. So if it launches from an airplane, launches from a balloon, if a bird drops a fish, whatever's going on, okay? If they ask for maximum height, they're typically asking above ground level.
So you said that the initial vertical velocity of 0, that's always the highest?
Then it means it's been dropped or launched horizontally. Yeah. Yes, always. Because there's only one place where the vertical velocity can be 0. And that's at that point where it reaches its maximum height. Because at max height, it's going from going up to going down.
And if it is going down, the same final velocity as the second before it hits the ground?
Yeah, so you can't put 0 for the final velocity when it hits the ground because eventually it will be, but that's not free fall.
And that second delta y is from the max point?
Yes, I kind of drew it. That's that delta y. So I hand. No? Seeing things? Okay.
Final could be 0?
The final could be 0. In this case, I set the final to be 0 because I'm starting here and getting to this point. Right? So the vertical velocity at that point is 0. Yeah. But when you put that 0 in for the y direction, you're telling the toolbox max height. There's just one problem, Mr. Balogh? Because we're coming up to an exam, it's getting closer, you need to know that if I gave a problem like this on the exam, I would only ask you for one part. Right? This was I can't, 78,000 boxes on the screen, right? We figured out a lot of stuff. I might ask you just for the max height above the water. Or the time it was in the air, right, on the exam. I'm giving you 10 minutes per problem. So I'm not going to give you a multiple part problem that takes 50 minutes to solve, right? Okay. So just realize that, right? Exam questions focus on one thing per problem and don't have multiple parts. All right, let's try. Oh yeah, let's do that. See where we get. Okay. Now, I know, big problem, all kinds of stuff, right? Okay. What I would like you to do right now is visualize this with each other for like the next 5 minutes. Start talking about it with each other. Start drawing the picture with each other. Start making the list with each other. See where you get stuck with each other. Because we need to talk about this. Go. If you and everybody around get stuck, call me over.
Yeah, and it's accelerated so the clip distance is 75 meters at 2.8. I do too. It just says exactly. Yeah, so there's an angle of 15. And the guy is like it's rolling backwards. So and then it goes down that way.
How did you do? Yeah? Yeah? Picture's worth 1,000 words, Mr. Balogh? What do you do to be able to, like, develop this skill? Being able to read and then put it into a picture? Practice. You just have to practice, right? I've given you, what, like 10 problems? I mean, there's some conceptual ones, but then like 10 problems that have words in them. Some have pictures, some don't. You have the entire end of the chapter problem set of practice. I'm not saying you have to do every problem. I'm saying you can read through the problem and try to visualize it. Just visualize it, right? And get that practice of just setting up a word problem and getting it into a picture or a list. And you can email me and say, hey, Mr. Balogh, did I set this up right? And go to the tutorial center, have them look at it. Oh, hey, did I set this up right? Okay? And get that feedback. So it's a matter of practice, right? In understanding some of the culture of a physics problem, like what do some of these words imply and meaning and all that kind of stuff. But in this particular case, right, you've got this angle and this car's heading down. Now, when it comes to the acceleration, is there a problem? Yeah.
The acceleration is going X and Y. You need to componentize it.
Oh dear. Okay, wait. Let's step back. How many accelerations are there? There's two. There's the acceleration this thing has when it's on the cliff. What did it say? 2.6 meters per second squared down the slope. Okay. And then there's the acceleration when it comes off the cliff. What's the acceleration it has when it comes off the cliff? Negative 9.8 meters, right? Okay. So the acceleration changes. Does this toolbox handle a changing acceleration?
No.
No. This toolbox requires a constant acceleration. So what does that suggest about what you have to do this problem? You have to do it in two parts. You can apply this toolbox to the first part, part A, the 2.6 meters per second squared, not part A in the problem, but like the first half, like the while it's rolling down the hill part, and then you apply the toolbox to the 9.8. If the acceleration changes, you have to break the problem up. Okay, so taking a look at the first part where the acceleration is 2.6 meters per second squared down the slope. Do I have to find components of acceleration? Do I have to find components of velocity? Do I have to find components of time? No, time's not a vector. Okay. But the answer is no. Because the part sliding down the hill is really a chapter 2 problem. What direction is the acceleration? Down the slope, isn't it? What direction is the velocity? Down the slope. What direction is the displacement? Down the slope. This is a one-dimensional problem. It is a chapter 2 one-dimensional problem where something goes a distance of 75 meters with an acceleration of 2.6 meters per second squared. Find out how fast it's going at the end. That's a chapter 2 problem. Yeah. Yeah, it starts at rest. Okay? That's a chapter 2 problem. And so, what's that chapter 2? It's a triangle, the thing. Okay, look at it, take your head, Oh! If all of your things line up along one dimension, it's a one-dimensional problem. The reason we have to break it up for when the car is in free fall is the car is moving in x and y, but the acceleration is only in y. And now we need vectors. But if everything's lining up along one dimension of motion, it's a chapter 2 problem. Even if it's tilted like that. So you do that problem, you find a final velocity, and that final velocity for the part on the hill becomes the what? For while it's in the air? The initial velocity for the part that's in the air. And then we break it up into components and we go. We're going to do that on Wednesday. We're going to pick up right here, and we're going to continue just doing example after example after example of projectile motion. I will see you then.